Okay. Hi everyone. So welcome to IGC classes for HAL examinations. So today in this class, I will be only taking up the problems from various chapters of analog circuit, right? So you will learn how to solve questions basically, from analog circuit, right? So today's class is going to be completely on problem solving session. So this is very important to attend. So I request everyone to attend this class or watch these sessions, which will be available on YouTube, right? So you can watch and learn how to solve, questions rapidly and what are the various techniques you should follow, right? Okay, so today's session is gonna be basically the problem solving session, right? Problem solving session on analog. Okay, so what are the chapter I'm gonna cover? So I'm going to cover various chapter. Basically, the very first chapter will be the diode, you can say. So the chapter from which I'm gonna take the problem will be the diode. Okay, already we have covered diodes. Okay, diode application. And second chapter is gonna be your bipolar junction transistor, right? BJT. I will be taking questions from small signal analysis as well, and I will help you to determine how to find the gain of any kind of amplifier, as well as how to find the input impedance and output impedance and so on and so forth, right? And then we will take questions from the frequency response of bipolar junction transistor, right? So the frequency response of, frequency response. Okay, frequency response, and then we will take problem from MOSFET, right? Metal oxide semiconductor feed effect transistors. So again we will discuss all the configurations, and then we'll take various problems from MOSFET and help you to solve questions, right? So I will give you brief history regarding MOSFET. Will introduce region of operation such as linear, cutoff and saturation. Okay, and in which region the MOSFET works as an amplifier. Those things I'm gonna talk, right? And the fifth will be the op-amp, right? Already we have discussed this topic in detail. The operational amplifiers, we will take PYQ of gate examination. So that those questions will definitely be helpful, to make strong your op-amp part, right? So whichever question you will find in HL examination, you would be able to solve, right? And then we will take questions from oscillators, right? Oscillator circuits, oscillators. And seventh one is going to be your feedback amplifier. So a few questions we will take from feedback amplifier. Okay, feedback amplifier. So hi Sobit, thank you for joining today. So today's session is going to be very, very interesting because I'm not going to talk the theory part of analog circuit. We will only, take up the problem solving. Okay, so you will learn how to solve questions from these topics which I have listed: the diodes and the bipolar junction transistor. Here we will discuss how to find the gain of any amplifier, and the frequency counterpart of the bipolar junction transistor. We will discuss MOSFET. Okay, where we will discuss all three regions of MOSFET, and then we will take all three configurations, common gate, common base, and common drain, and we'll try to find gain and all, right, by inspection, without drawing in fact the small signal analysis, a small signal model, because that is only required to solve the question within 40 seconds, right, in the examination. Suppose any amplifier is given, and if you draw the small signal model, and then it will take a lot of time. But if you know the concepts, okay, and we'll take problem from op-amp, oscillators, feedback amplifiers, okay, and so on and so forth. So these are the major topic, and today I'm gonna take class for 3 hours. So please, pay your attention, right? Okay. So let us go and right? So I'm going to start from the diode circuit. Already we have discussed diode application. Okay, so please pay attention to it, right? So the very first question on your screen is from GATE 2003. Okay, the circuit shown in the figure is best described as, right? And there are four options: the bridge rectifier, the ring modulator, the frequency discriminator, and the voltage doubler, right? Okay, so see, this time they have given the question and they are asking you to identify this circuit. So, Sobit, can you tell me which option is going to be correct for this question if you are able to hear me? Yes, are you able to hear, Sobit? So, can you answer this question? The question number one, which I'm going to answer here, is that already we have discussed various things, right? So, anyone can answer this question. You can consider that the input is given here as the AC input, right? AC input is given. Okay, so whenever in the positive half cycle and in the negative half cycle, what will happen? And you are taking the voltage across. You can see you are taking the voltage across. Uh, you have got only two elements. One is capacitance and one is diode, right? So please identify this circuit, and you can comment also your answers, right? Uh, because I will be taking up good questions from diodes. Yes, anyone can answer this question. Okay, so this question is very familiar to us because this cannot be the bridge rectifier because there is no, uh, a resistor and all, right? And bridge rectifier demands four diodes. Okay, so bridge rectifier must have the four diodes, right? Bridge rectifier. Okay, bridge rectifier. Okay, it needs four diodes. Okay, so this cannot be the option, right? Ring modulator, it cannot be the answer. This frequency discriminator, it cannot be. Only voltage doubler. Okay, it is a voltage doubler circuit, remember. Already I have told you how to design voltage doubler circuit. So let me explain again the voltage doubler circuit, right? So the voltage doubler circuit. Already I have told you that you can put here the supply, and you can connect the diode like this, right? And the diode like this, okay? And then you can connect the capacitance here, right? Already I have told you how to design doubler circuit. uh okay, so when we were talking about clamper and peak detector, right? So if suppose this kind of a circuit is given, right, and the supply is this, okay, and if you're finding the output across diode, right, if finding output across diode, then you can say this is a clamper circuit, right? This is a clamper circuit. And if you're taking, suppose this kind of a circuit is given and you're taking output across the capacitor, right? Okay, if you're taking output across capacitor, right? So you can say that it is a peak detector circuit, right? Peak detector. So this is what I wanted to highlight. So this is a voltage doubler circuit. How it is voltage doubler? You know that this capacitor will charge in this direction. You can say the plus to minus it will charge. Suppose the input is given as Vm sine omega t, so it will be charged up to Vm, right? And then this diode will be open circuited, right? So then this capacitor will charge from this to this. You can say that this will be charged up to 2 Vm, right? Okay, because you will apply one uh, you know 1 kVL, right? So this is a doubler circuit, you can say 2 Vm. Okay, right. So let us take next question because this question has got answer. doubler circuit. So please, whenever you study the analog circuit, you have to identify as well, right? Identification is very, very important, right? Again, let us take next question from diode application only. So the question here says that the diode and the capacitor in the circuit soon are ideal, right? The voltage Vt across the diode. Okay, so in the question itself, they have mentioned that you have to find the voltage across diode. Okay, across diode, finding voltage, finding, okay, finding voltage across the diode. What does it mean? Finding voltage across diode means it is a clamper circuit, right? It is a clamper circuit, remember. Okay, so here what we are doing here is you have to find the voltage across the this diode, right? So what will happen initially that this diode will turn on, right? So this capacitor will charge up to 1 volt, right? You have to, because the amplitude here is 1 volt, right? So this capacitor will charge up to 1 volt, okay? And then you can what, you can remove this capacitor, because I have told you two-step process to solve any clamper circuit problem, right? The first step is going to be find voltage across this Vc, find Vc, and second, open circuit diode, right? Open circuit diode and find output, right? So this 1 cos omega t. So your initially your diode will be on and your capacitor will charge up to 1 volt, right? And then forget about this diode, right? So across this, you can say that across this plus to minus, okay, you can apply 1 kVL, right? 1 kVL. So we can write here by KVL, by KVL. See how easy this question is. This question was asked in GATE 2012. So by KVL, we can write here minus cos omega t, and this is plus 1, okay, plus Vt, right, equal to 0. So your Vt will be, which is the voltage across the diode. Vt will be what? 1, this will be what? This will go that side, so it will be plus, and this is minus, right? So let me erase here. Okay. So this will be cos omega t minus 1, right? So which option is going to be correct? Your option A will be correct for this question, right? So this question is very easy question, okay? So you can see, right? So if you want to talk about this circuit, so this part of a circuit, okay, if you are finding or measuring voltage across the diode, so this part of a circuit is known as clamper circuit. And if you're trying to find the voltage across this capacitance, right? Suppose someone is going to ask you what is the voltage across this capacitance. So this part of a circuit is will be what, the peak detector circuit. And combining the two, you can relate again that you might get voltage doubler, or okay. So please, identification is very important. I hope this solution is understood, right? Okay, let us take the very third question, right? The third question again from the diode application. So let us read the question. If the circuit shown has to function as a clamping circuit, then which one of the following conditions should be satisfied for sinusoidal signal of the period t? Okay. So you can see here they have already told you that this circuit is basically a clamper circuit, right? This circuit is basically a clamper circuit, right? And what is the meaning of clamper circuit? Clamper circuit basically does what? The DC does add DC to the AC waveform, right? So I have told you two-step process to solve the any clamper circuit problem, right? The first step is gonna be what? Find Vc, find voltage across the capacitor, right? And second one is open circuit diode, right? And find output, right? Find V out. And the third very important condition which I told during the class is important condition, right? See, once the capacitor is charged, you don't want this capacitor to discharge, okay? Because this capacitor will store DC, okay? This capacitor will store DC. You can say there is a V. V means what? Vm sine omega t. You can say Vm sine omega t, right? So this capacitor will charge up to Vm. Okay, we can say Vm, right? Vm. Wait. You can say this capacitor will charge up to Vm, right? So once the capacitor is charged, this DC has to be added with this AC waveform, right? So you don't want this capacitor to discharge, right? So your discharging time constant, right? Discharging time constant should be far greater than the time period of the waveform, right? Time period of the waveform. So this is very important condition, right? Your discharging time constant should be very high, right? And what is the discharging time constant here? RC, right? Once this is open, so your capacitor will be what? Your capacitor will start discharging through this R, but you don't want this capacitor to discharge. So this is very important condition for clamper circuit. This is very important condition for peak detector as well. So RC must be far greater than T. In fact, you might have studied in communication system also the envelope detector circuit, right? So this is very important condition. The charging time constant of a capacitor should be very less, right? T charging, okay. T charging should be very less, no problem. Okay, T charging should be very less. It's okay because you want your capacitor to charge immediately, right? You want your capacitor, you can say 0, right? But this is discharging time constant, and it is very important. So your option for this question will be what? Option D, right? So this is question number 3rd from the diode application, and this kind of question only you can expect in the HL examination, where you don't need lot of time to solve the question, right? And directly you can hit the answer. And the question 14, right? I mean question number 4th from the diode application again. The diode D1 and D2 in the figure are ideal and the capacitors are identical, remember, okay? The product RC is very large compared to the time period of the AC waveform. See, in the question itself they have mentioned the very important condition, RC must be far greater than capital T, right? This question was asked in GATE 2016 by IISc, right? Okay. So please make sure that read the question properly. Please make sure that read the question properly, right? Welcome Surajit in the class. So today's class is gonna be completely on problem solving session, and I have already taken few problems, right? So you can go through recorded session, but let us begin from question number 4, right? So this question number 4 is very important. Let us read the problem first, okay, for you. So what question says here is that the diode D1 and D2 in the figure are ideal, right? Okay, the ideal means what? That diode, if diode is conducting, so it can be replaced by short circuit, right? This can be replaced by short circuit, and if the diode is not conducting, it can be replaced by open circuit, right? So remember, this is the meaning of ideal, that's it, right? And they have mentioned the important condition, the necessary condition for clamper circuit and the peak detector circuit. You can see the the product RC is very large compared to time period of the AC waveform. Okay, this RC, this time constant is basically the discharging time constant. Okay, T discharge, remember, must be far greater than capital T, right? That RC must be so that your capacitor will not discharge. Okay, your capacitor will not discharge once it is charged, right? Okay, and assuming that the diode do not break down in the reverse bias, right? Okay, this diode should not break down in the reverse bias. Okay, if you will increase the reverse bias condition across this, so PIV rating, you might have studied about PIV rating, peak inverse rating. Okay, the output voltage V naught at the steady state, you have to find the voltage across this. Okay, if you are trying to find the voltage across this, means that you are trying to find the voltage across this capacitor, right? So your capacitor, this the top capacitor will charge like this, right? So you can say plus to minus, this will charge, and this capacitor will charge from plus to minus. Okay, Basically, you're trying to find the output across the capacitor. What does it mean? This is a circuit. This is a what kind of circuit? This is a peak detector circuit, you can say, right? As I told you that if there is a diode and capacitor combination, right? Okay, this kind of a circuit is given for you, and if they are asking you to measure the output across this capacitor, right? So this circuit is known as what kind of a circuit? This circuit is a peak detector circuit, and they have identifying the circuit is very important for PSU examinations, in fact in real life as well. Okay, it's not all about examination only. You must be able to identify the circuit so that it will help you to determine the determine what the answer very quickly, right? So this capacitor will charge like this, so plus to minus. Okay, so this capacitor will charge up to what, as we know that this charging time constant 0, because this diode is ideal, so this diode will not offer any resistance, so R times C will be 0 right here in this case when the diode will be on, right? When diode will be on, plus to minus in the positive half cycle, this capacitor will charge up to 10 volt, right? You can say 10 volt from plus to minus, right? And this diode, once this diode will turn on, right, so it will again charge from plus to minus, okay, that 10 volt, right? So what is the voltage across this? The voltage across this will be the sum of these two voltages, right? So the steady state voltage is what? V0 will be what? This is plus to minus, that is 10, right? And this is minus 10, right? So the total voltage will be what? 0, right? So this is the answer for this question. The 0 will be the answer, okay? It was very good question for 2 marks, okay? This kind of question you can expect in the exam. So you don't need any network analysis or anything, only just need to know what is the important condition for clamper circuit. So this is the important condition. In the last question also the same. See, in this question they have asked the condition itself, right? If the circuit shown has to function as a clamper circuit, then which one of the following condition should be satisfied for sinusoidal of for sinusoidal signal of the period t, right? So this was the condition. RC must be the product RC must be very greater than the capital T. Understand? So most of us focus on only solving the question. We do not take care of what are the important conditions for clamper circuit, when clamper circuit will behave like a clamper circuit, right? I hope, Surajit, are you able to understand this question? Okay. This question, are you able to understand
Yes, sir.
the solution?
Yes, sir.
Please let me know. My voice is audible for you?
Yes, sir. Audible, sir. You're audible.
Right. Let us go to next question. So this question is based on from our first class itself, right? So which of the following are the correct for basic amplifier configuration, right? So there are few configurations given, right? So if you have studied taken my class, that first lecture on the YouTube itself, right? Amplifier modeling, okay. So I have told you various you know trick and methods to remember these kind of or answer these kind of questions, right? So which of the following statements are correct for basic amplifier? This question was asked in 1990, right, way back. So the common base amplifier has low input resistance and low current gain, right? The common collector has very low output impedance and high current gain. Common emitter amplifier has very poor voltage gain but very high input resistance. The current gain of common base amplifier is higher than the common current gain of common collector amplifier, right? So already I have told you that the common collector amplifier is basically what? The voltage amplifier, right? Common collector amplifier is basically the voltage controlled voltage source amplifier, and we know that if the voltage amplifier is there, the Rin, okay? If the voltage amplifier will be there, then Rin will be what? Rin. Rin will be high, sir, right? And R out should be R out should be what? R out should be low, sir. Okay. And as far as this is a common common collector circuit, it is also known as emitter follower. Emitter
So
follower, right?
is
These are
it
the
a
information
MSQ question?
only. Okay. So R in must be high, R out must be low, and if it is a voltage amplifier, you can say it can be also the voltage buffer circuit, right? And the voltage buffer has the voltage gain very close to unity, but the current gain will be high, right? But the current gain will be high, okay? In case of common collector, the voltage gain will be very close to, voltage gain will be very close to unity, but the current gain will be high. Then only your power gain, overall the power gain matters, right? In case of op-amp, in case of amplifiers, so this will be equal to ai. Everything I have discussed, right? So from this discussion you can take you can eliminate options, right? So what they have told here is that the common collector a common collector amplifier has, you know, low output impedance. Yeah, it is correct. And high current gain. So this B option is correct here, right? And let us talk about common common base amplifier as well, right? Common base amplifier as well. Let me discuss common base as well, right? So the common base amplifier means common base amplifier can be taken as CCCS, okay, or you can say the current amplifier. Okay, current amplifier, right? What is the meaning of current amplifier? It has R input. R input will be low and R out will be high. Everything I have discussed. And if you consider this current amplifier as a current buffer, so you can say that the AI will be approximately 1, right? Your current gain for the current amplifier will be approximately 1 and your voltage gain will be high. Okay. So your overall power gain will be approximately equal to the voltage gain only, right? So what they have given here is, let us read. Okay, let us read now. Right. So let me read the options again based on this discussion. So the option says here is that option first, common base amplifier has low input impedance and low current gain, right? Yeah, yeah, it is correct as well, right? Common base amplifier has low input impedance. Yeah, it is correct, and low current gain, right? And in case of option D, the current gain of common base amplifier is higher, right, than the current gain of common collector amplifier. This is wrong, because common collector has the current gain high compared to the current gain of common base amplifier. This is correct, wrong. And common emitter amplifier has very poor voltage gain, right? So this is also wrong, right? Because common emitter has everything, like input impedance, output resistance and gain, and everything will be in intermediate range, right? So your option A and option B is correct for this question, right? So I hope this is clear for everyone. So your option A and option B will be correct. So this is kind of MSQ question, right? Multi-answer question. Okay. So if you know these discussions, so you can easily answer the question, right? So Surajit, have you understood this question?
Yes, sir.
Okay, so let us go to next question, right? We will take up again more problem from diodes and BJT and everything. But what I have done here is whatever topics I have, whatever topics I have covered, I'm solving for them. And then after discussing these important problems, we'll start again the diode and the bipolar junction, then op-amp, then more MOSFET. Okay, right.
Okay.
So consider the circuit shown in the figure. If you have studied or taken my lecture, last lecture of the analog circuit from HEL season, right? So this question can be done very easily. Consider the circuit shown in figure assuming BE1, the base emitter voltage, and the BE2, okay, EB2, 0.7, the value DC, the value of DC voltage Vc2, here we have to find, right, Vc2. Okay, so what you can do here is that if you have got 2.5 here, right, so the voltage across this guy is what, you can answer this question on this question itself, right? So the point plus minus, okay, 0.7 is here, right? So you can determine the potential at this point. What will be the potential at this point? This kind of a transistor is known as also the diode connected transistor, right? Because see, the base and the collector is connected. Okay, so this is basically a diode connected transistor, you can say. Okay, this is a diode connected transistor, remember. Okay, so whenever question is asked in the examination, you guys start attacking on the question. You do not understand why this transistor is connected and what is the reason and what kind of transistor is this, right? Okay, okay. So now this 0.7, okay, so 2.5, and if you will subtract, because you are going down, right, as I told you, whenever you will come down, okay, so you have to subtract from 2.5 minus, so you can subtract here 2.5 minus 0.7. So what voltage will be here at this point? You can say VE1, or you can say this is VE1, right? VE1, or you can say VE2 as well, right? Because this terminal is sorted here, right? So this will be what? 1.8, right? This is 1.8 volt, right? And again you are coming down here, so you can see this is again 0.7 volt is down, right? So 0.7 volt is down means what? 0.7 volt is down means the potential at this point, right? The potential at this point you will come to know. So you can say the VB2 will be what? VB2 will be 1.8 minus 0.7, right? So 1.8 minus 0.7 means what? 1.8 minus 0.7 means 1.1, right? Okay, yeah, 1.8 minus 0.7 means 1.1. And now what you can do here is you can find the base current, right? You can find the base current here, and then you can find the collector current, right? So once the collector current is known here, okay, once the collector current is known here, so you can find Vc2, right? So what is Vc2? Vc2 will be IC2, okay, IC2, right? Let me write here the IC2 into 1 kilo ohm, right? This is the answer, right? So we need to find IC2, okay? So please try this question. This question is very good question, right? So you can answer this kind of a questions. So yes, so VB2 here, the potential at this point is known, because the potential at this point is 1.8, and if again you are coming down, right? So you have got 1.1, okay, 1.1, yes. So 1.1 volt is there, right? So now you can write IB. So this current in this direction you can find the current. So you can say that IB2 will be what? 1 minus 1.1, right? 1 minus, okay. So you can say the current here will be what? In this direction, right? In this direction. So this is bigger. So 1.1 minus 1 upon the 10K, right? This is IB2. So IB2 will be what? IB2 you will get here is approximately 0.1 upon 10 kilo, right? 10 kilo. So you can take this kilo up, okay, and 0.01 milliampere, okay. You can say 0.01 milliampere current is there, IB2, right? And now what you can do here is, now what you can do, you can once you know this, so what is IC equal to IC2 will be what? Beta 2 times, okay, beta 2, right? because beta IB, you know, right? The relation which is valid for active region. So beta 2 times IB2, right? So you can see here it is 50 times, okay? Because in the question they have given beta 2 as 50. 50 times 0.1 upon 10 into 1000, right? So here you can cancel 0, 0, right? And now you will see here is that this is what 0.5, okay, 0.5 milliampere, right? Once you will plug here 0.5 milliampere, right, into 1K, so it will give you 0.5 volt. This was very easy question, right? This was very easy question, so you don't have to worry about that, right? So 0.5 is the correct answer for this question. I hope this is clear for everyone, okay? Right. So let me go to next question, and so this question can be done from my previous lecture, right? So if you are good at everything, so please try to solve this question, okay? Let us take one more problem, okay? So this problem belongs from the lecture number 1, right? If you have seen my lecture number 1, so you can solve these questions very easily. So let me read the question here. The cascade connection of two voltage amplifier, right? They have given two voltage amplifier, or you can say Vcvs they have given, right? One, and they have given Vcvs, right? The loop gain of okay, AV naught and Rin for for first voltage amplifier and second amplifier, right? They have given everything here. You can see all the information they have given, and you have to find the approximate overall voltage gain V out upon V in. And this question was asked in GATE 2014, right? So this kind of question you can expect in HAL examination. So nothing to worry about here, as we know that the equivalent model of Vcvs, right? What is the equivalent model? What is the equivalent model of Vcvs? So we know that uh, any amplifier will be having its input impedance and output impedance, right? So this is input impedance of first amplifier, and this will be replaced with dependent sources, you know, because the voltage amplifier means dependent sources only. Amplifier can be modeled with the help of dependent sources, so that's why I'm using here the dependent sources, right? So let me draw a slightly bigger circuit so that things can be accommodated, right? So this is what the circuit picture, okay, plus minus this will be what the K times, okay, K means this open loop gain times the VE1, right? So 10 times V in, okay, V in 1, okay, and this amplifier will be having output resistance. Output resistance is 1, and this input resistance was what, 10K, right? And this is what the, okay, so this is the input port, right? And output resistance is 1K here. Now A2, so A2 will be having the input resistance. So you can say the A2 for A2, right? For A2, the input resistance will we have like a load for A1. So this is a part for A1, right? And now we are connecting A2 here. So I mean input resistance for A2. So this is 5K. Okay. Again, you have to place one dependent source. As I said that the amplifier can be modeled with the help of dependent sources, right? Okay, so here you can say it has output resistance as well. So output resistance is 200 ohm. Okay, and and now load is connected here, so you can connect load, right? What is load here? Load is basically 1000, so 1K, right? And the output will be what? Output will be across measured across this 1K, right? Okay, so this part of a circuit is basically the amplifier circuit A2, okay, and the V in 1, right? And this has the gain that is 5, and whatever output here will be, right? So you can say V out 1, okay, and this is V out 2, you can say, but it's okay, no problem is there, right? So you know, so you can see this V in is directly applied to this, so this will be here the V in, okay, so across this is V in, okay, right? So now we have to solve this question, and this question can be done very quickly. So this then V in will be here, okay, if any input is applied across any resistance, so this resistance has no importance now. So directly you can jump here and you can find you know, V naught 1, right? So what is V naught 1? V naught 1 by voltage division rule, okay? So this question is very easy. So why, you know, voltage a division, right? By voltage division, you can apply here. V naught 1 equal to, right, that is you know, 5 into 10, or you can say 50 V in, okay, you can say V in or no problem, right? So just forget about this subtract, so okay, this is V in only, right? So 50 V in upon 50, right? Because 10 into 5, that is 50 V in upon 6, right? Upon 6, because 5 plus 1, that is 6. So this is the V naught 1, right? This is V naught 1. Now you can plug here, right? So, and you can directly find out the, okay, so by voltage division at output node, output loop, right? So by voltage division again, okay, at output port here, right? So your V out equal to what? Your V out will be equal to 5 V naught 1 into 1, right, upon 1.2, right? So this 200 can be written as 0.2 K, okay? So now you can plug this, this is equation number 1, you can take and you can plug everything here, right? So from here just I'm going ahead. So V naught equal to 5 by 12, right, into, so not 12, 1.2, okay, 1.2, 5 by 1.2 into this V naught 1. What is V naught 1? That is 50 by 6, right, V in. So from here V naught by V in will be what? V naught by V in will be 25 upon 7.2, okay, so you can solve now this, okay, and you can answer this question, right? So this will be the approximate answer for this kind of a circuit, right? So please solve this and you will get the answer, right? 250 by 7.2. So I hope this is clear for everyone, because if you know the circuit, I mean, if you know the equivalent of these amplifiers, right? If you know the equivalent of these amplifiers, okay, A1 and A2, so you can draw the equivalent, right? Okay, amplifier, then draw its equivalent, then okay, apply some KVL, KCL, right? Voltage division rule, and get the answer, right? So needless to worry about any question, right? So this question was very good question, I think. I hope this is clear for everyone, right? So let us go to next slide. And now we will start again taking questions from diode and then VJT, okay, and then so on and so forth, right? So let me complete all the questions from diode, then VJT, Okay, because today we will be only focusing on the problems. So I hope these are few problems, around 10 problems I have discussed. You can see here. So from the first, I took this problem and we asked you to identify this circuit, right? And I told you also how to identify circuits, right? So please take care of that. And the question number 2 was again the combination of clamper and peak detector. And here this was the condition they have asked, the important necessary condition to be have any circuit as a clamping circuit. Okay, and these are the problems. So see how quickly, and this problem is very good problem, right? So please try to solve this kind of problems. Okay. Okay, and this problem also we have done here. So this Vc2 we need to find. So the answer was this 0.5. Okay. Apply, and I have told you the trick. So let us take the problem from diode again, right? So here I'm gonna write some problem from diodes and we will solve, right? Then we'll take problem from BJT and solve. Okay. So one of the problem was from a small signal analysis, right? Questions, okay, from a small signal, right? Analysis. So what question says here is that, the question says that in the circuit shown below, right? In the circuit shown below, so you can write the circuit, draw the circuit. In the circuit shown below, assume that the voltage across forward biased diode is, okay, you can say V gamma is given as 0.7, right? Voltage drop across the forward bias diode is this, and they have given Vt. Vt was given as 25 millivolt, right? At the rate we know that is 300. Okay, okay. And the in small signal input, right? And small signal input, that is Vi is given as Vp cos omega t, Vp cos omega t. Okay, where Vp is, okay, where Vp is, right, where Vp is what, the 100 millivolt, 100 millivolt, right? You can say 0.1. Okay, so this was the information given in the question, right? This was the information given in the question. And now let us draw the circuit for this question, right? So circuit here is like this. Okay, so you can draw the circuit along with me. Circuit, so they have given the DC plus AC, right? DC plus AC. Why they have given DC plus AC? Because we want my diode to work in linear region, right? So this is input, okay? DC plus AC. So DC voltage will be given to find out or calculate the diode current, okay? And AC voltage will be given, find out what? The overall output, right? So see, there are 4 diodes, okay? One diode, second diode, okay? And the third diode and the fourth diode. So this kind of a configuration is given, okay? And the input is 12.7 and Vi, and this is given as 9900 ohm, right? And you have to find what? The number one question is what? Number one is the bias current IDC. The bias current, okay, the bias current IDC through the diodes, right? Through the diodes, okay, each. So this is first question. Let us solve this problem first, okay? And they have given some options, okay? So options are like, you know, options A, B, C, and D. What option they have given here is, they have given 1 milliampere, they have given 1.28 milliampere, right? And they have given 1.5 milliampere, and they have given 2 milliampere, okay? So let us solve this question, right? So once the diode is on, this diode will be replaced with what? This diode will be replaced with 0.7, right? Because the on voltage is 0.7, okay? So initially you can find the IDC. How can you find IDC here? So you can say that we are in the positive half cycle, and this diode will be on, right? All the diodes will be on. So we can replace them by short circuit, right? Not short circuit, because they have given the battery, okay, on voltage. So you have to replace these diode with this kind of a battery, right? This kind of a battery. How many batteries are there? There will be 4 batteries. So total voltage will be 2.8, okay? Total voltage will be 2.8, right? So let me draw the circuit here for, okay, so the DC analysis. The first is DC analysis, okay? Consider DC analysis. So for DC, IDC we have to find out now. So this is 12.7, right? Let me raise this and write properly. This is 12.7, okay, plus minus DC voltage, and this is 999, okay, and your this will be what? There are 4 voltage sources, right? I mean 4 batteries will be there, so you can say 4 times 0.7. Now you can find the I, okay, I from here, ID. So what is ID here? ID will be, directly you can find, that is 12.7 minus 2.8 upon 9900, right? So you can approximately give me the answer here, IDC. What will be the IDC for this question, right? Okay, IDC for this question. So IDC will be approximately 1 milliampere, right? 1 milliampere. Okay, once you will solve this, so you will get 1 milliampere. Okay, so what is the answer for this question? First question, you can say that the answer for first question will be 1 milliampere. Okay, okay, so whenever you will perform DC analysis, only purpose to find DC IDC is to find the AC current, sorry, AC resistance. Okay, because you know that the RAC will be what? RAC will be eta Vt, right? Or you can say eta. If eta is not given, so you can say Vt upon IDDC, right? So what is Vt here? That is 25 milliampere, and what is IDDC? 1 milliampere. So this will give you 25 ohm, right? So now second question they have asked here is what? Second question they have asked is the AC output voltage. The AC output voltage. AC output voltage, right? So V out AC. So what will happen now? You will have to perform the AC analysis, right? So what is AC analysis? AC analysis means your diode will behave like a resistor. Understand? A small signal model already I have discussed. So now your circuit becomes, there is a AC circuit, AC, that is input VI. Okay, and resistance will be same, that is 999900. Okay, 9900. Okay, or 9.9 kilo you can write, no problem, but still you can write 9900. Okay, now there are 4 diodes, 4 times of 25, right? You can say 4 times of 25 ohm. Okay, already we have computed the resistance. Okay, and you have to find what? The V out, and the AC voltage is what? Vp something, you know. What is AC voltage? That is Vp cos omega t. Vp cos omega t. What you can do here is you can first apply the voltage division rule. By voltage division rule, okay. By voltage division rule, and the V out will be what? V out will be 100. Okay, 100 times Vi upon you can say this will be 1000. Okay, so 1000 here it will be cancelled. Okay, two zeros. It will be Vi by 10. Okay, it will be V out equal to Vi by 10. So now you can plug back the Vi. Vi is 100 millivolt. Right. So here I am writing Vi is 100 millivolt. So 100 millivolt cos omega t, right, upon 10. So this gets cancelled. This is 10 millivolt, okay, cos omega t, right? So this is perfect. This is perfect, right? Cos omega t. So from here you can solve, okay. So you can write here is that this will be 10 millivolt cos omega t, okay. So your option will be the options where this is present, right? Wait, 1 minute. That is 100. Okay. Right. This is 100 plus this 1000, right? So Vi by 10. And let me correct. I mean, if anywhere any kind of mistakes happen, so please take care of that. Okay. So the answer will be what? Yes. So this is 100 basically. Okay. So this is 100. And so Vi into 100 upon 999 and plus that. So 100 upon 1000. And what is Vi? Vi is basically 100 cos omega t, right? 100 cos omega t. Yes. So this will be the answer. You know, 100 millivolt cos omega t upon this. So this will be 10 only, right? So let me, you know, again try this question anywhere, any kind of mistake, right? So your V out will be what? Your V out will be 100 into Vi upon 900 plus 100, right? So it is giving you 100 Vi upon it is 1000, right? It will not be 1000, it will be 10,000 because there is 9900. So please take care of that. Okay, please take care of this. Here is the mistake. Okay, so please take care of that. This will not be 1000, this will be 10,000. Okay, so the answer will be, I mean, 1 millivolt only, right? 1 millivolt. Okay, remember, so there will be 100 again. I mean, this will be 100. Okay, this is 100. Okay, so the answer for this question will be what? 1 millivolt. Please remove this one, 0. Okay, so the answer for this question will be 1 millivolt, right? So please correct that. Okay, because 9900 plus 100 means 10,000. Okay, so let me write here properly. So this is what the picture is. So 100 gone, and this is 100 millivolt cos omega t upon 100. This answer will be 1 millivolt cos omega t. Okay, so this is the answer for this question. Right. So I hope this is clear for everyone. This question was from a small signal analysis, so please take care of that. Okay. Very good questions. Right. One more question. No, question number. Okay, next question from the diode. Diode in the circuit given below has. Okay. Diode in the circuit. In the circuit given below has. Given below has V on. V on equal to what? 0.7 volt, right? V on equal to 0.7 volt. But is ideal otherwise, right? But is ideal otherwise. The current, you have to find the current. The current in milliampere. Very good problem, right? The moment you see the problem, you can solve. In the 4K ohm resistor, right? In the 4K ohm resistor H. Okay. So this is a problem. Okay. And here is the circuit. So let me draw the circuit. The circuit shown here is like this. There is a current source. Okay. Which is exciting. Okay. And there is a bridge kind of a network, right? So here resistances are connected. Okay. There are 4 resistances connected like this, right? And there is a diode in, there is a diode here. Draw properly. So here's the diode. Okay. Yes. So what are the resistances connected here? Let me draw that as well. Please draw the circuit perfectly, right? Like this. Yeah. So let me choose the black one, and we know that this is 2K and this is 3K and this is 6K and this is 4K, right? And this guy is having 1K resistance, and the 1 milliampere current is having the source as 1 milliampere current. Okay. So now what you have to do here is, whenever the bridge kind of a circuit is given, okay, and you have to find the current through this 4K, right? So whenever bridge kind of a network is given, so you have to check whether this bridge is balanced or not. So by looking at this, if you multiply 6K into 2K, that is 12K, right? So what we found here is that bridge is balanced. Bridge is balanced. How we are saying 6 into 2 equal to 4 into 3. That is 12 equal to 12, right? So if bridge is balanced, so this will be completely open, right? Open circuited, right? Here to here, no current will flow, right? So this 1 milliampere current will be divided in 2 branches, okay? Remember, so we can draw this. This is simple network problem then, okay? Because the current will not flow here. The current will not flow here, okay? Because this diode is what this bridge is balanced, basically this network is balanced, okay? So we can redraw the circuit, okay, for balanced one. Now this is the resistance, and this is simply a current division problem, current division rule, okay? Here you can apply. These are the resistances. So this is 2K and this is 4K and this is 3K and this is 6K. So current you have to find through this guy. So by current division rule, 1 milliampere by current division, by current division. what will happen here is that suppose this is I1, you have to find I1, right? I1 equal to total current, that is 1 milliampere, into opposite sum of opposite resistance, that is 9, right? So here you can say 9 upon total resistance. What is total resistance here? Total resistance is 6 plus 6, that is 12, plus 3, that is 15. Okay, 12 plus 3 means 15. So you can cancel out now. So it will be 3 ja, right? And this is 5 ja. Okay, so this will be 0.6 milliampere, right? Because this goes up to okay, so this will be 0.6. Understand? This is 0.6 milliampere current you will get. So I hope this question is understood. This solution is understood. Okay. So what you have to do here is, whenever the circuit is given, bridge kind of circuit, so make sure that if I mean, check before you attack on the question that the bridge is balanced or not. Okay. Very good question. Right. So let us take one more problem. Okay, from the diode circuit only, and we will be taking today many problems from diode circuits. These are very good problems which I have seen, right? Yes. One question was there from the circuit, right? They ask you to find the output waveform, right? So for the circuit with the ideal diode, for this circuit, okay, for the circuit with ideal diode, okay, shown in the figure, shown in the figure, the shape of the output, okay, the shape of the output, or you can say V out, for the given sine waveform, for the given sine waveform, input V in, okay, will be, right? So for the circuit with the ideal diode shown in the figure, so let us draw the circuit first, okay, because we're talking about circuit, so there should be a circuit, right? Circuit looks very interesting, right? And there is a cross coupled diode connected, right? Cross coupled diode connected here. So this is connected from this, and this guy is connected here. There is a diode again. This is connected, okay. And here you can see there is an input applied, V in, right? And there is a sinusoidal input, okay. One cycle they have given. So this kind of an input is given, right? From 0, and this is capital T. This is V in. Right, and there is a resistance, and you have to find the voltage across this guy, that is plus to minus V out. Okay, and they have given some options. So the option A is given as input, as it is input, right? Option B is given as, they have just reversed it, okay, up to T. Half is 0.5, okay, at this point it will be 0.5 T, and the waveform is, output versus that, okay. And option C is given as this, and it will be 0 onwards, till 0.5 it will be on, right? And D option is they have given here is it will be 0 initially and it will be like this. Okay, so this is the output waveform. You have to choose it, right? So this question is very easy question again, because you have to check whether the diode is on. Already I have told you, suppose this is 0.5 capital T, right, T by 2. So for the positive half cycle, for positive half cycle, it will be connected like this, plus to minus. So this diode will be on and this diode will be off, right? This diode will be on and this diode will be off. Let me check whether the diode the diodes are connected like this only. Wait, yeah. So you have to change this. Please correct that because this diode is not pointing toward output. This diode is pointing toward input only, like this. Okay, so please correct that. So this is a circuit given in the question, right? So for positive half cycle, this diode will be on because this positive terminal is connected with P type, okay, P terminal, right? So this is on, and again this diode will be on because this N side is connected with negative. So both diode will be on, right? So this plus will be transferred here and this minus will be transferred here, right? Because see, this diode will be on, so this plus will be here. I mean, if there is a if you are applying here this kind of a waveform, right? Positive half, okay, positive half of the waveform. So there will be inversion because these two diodes are connected. Okay, cross coupling is there, right? So this plus will be here. This, okay. So your output will be what? This cannot be the output, right? Because whenever you will apply plus positive half cycle, so there should be inversion, you can see. And this, this cannot be the answer, right? So this option can be correct, option C, right? Because when you are in negative half cycle, so this diode will be on off, okay, and this diode will be off. So for the negative half cycle, both diodes will be off. You can write here for positive half cycle, both diode are on, right? Both diodes, very good problem. Both diodes are on, okay. For negative half cycle, both diodes are off. Therefore, V out will be 0. Okay, in that case, here the V out will be equal to minus V in, right? From 0 to 0.5 capital T. Okay, so your option C will be the correct answer for this question. Okay, so please take care of this. It is very easy question. Yes. All the questions which we are discussing here is very good question only, right? So please make sure that you are like you can do these kind of questions. Okay, so let me take more problem now from op-amp circuit, right? Now we will take questions from op-amp. Okay, then we will take problem from bipolar junction transistor as well, and Mosfet. At the end, Mosfet we will discuss. So these are PYQ questions, and previous year questions are very important, right? So please make sure you are capable of doing, okay, quickly. Right. So the question here says that in the given circuit, if the voltage input, okay, let me write the question here. In the given circuit, in the given circuit, if the voltage input I mean V negative and V positive are to be amplified by the same application factor, amplified by the same amplification factor, amplification factor, the value of R, the value of capital R should be. This is a question, right? And circuit we need to draw now. Okay, so in the circuit you have to read the question very carefully, right? And you can answer this question if you have attended my class. In the given circuit, if voltage input at inverting and non-inverting are to be amplified by the same amplification factor, the value of R should be, you have to find, okay, the value of R should be. So let me draw the circuit here. The circuit given here is like this, that is minus plus, and there is a resistance connected. Okay, this is R which is unknown. Okay, this is R which is unknown, and this guy is there is a feedback resistance as well, right? So this is V out, and your op-amp is ideal. Remember, this is ideal op-amp. Okay, this is V minus, this is V plus, and the resistances are like 10K, and this guy is 15K, and this is 22K. Okay, so this is a circuit. In the circuit shown, if the voltage input V negative and positive are to be amplified by the same amplification factor, the value of R should be. We have to find the value of R, that's it, right? So how to find value of R? They have given everything. So both are the inputs, right? V negative and V plus. There are two inputs, so we have to apply superposition, right? And we have to find the amplification factor for each. What is amplification factor of any amplifier, right? You must know all these things, right? So see, if I talk about any basic amplifier, that is inverting amplifier, right? Or non-inverting, you can say inverting, okay, amplifier. So what is the gain here? V out upon Vi equal to 1 plus Rf by R1, you can say, right? So this is basically the amplification factor, right? This guy is the amplification factor. In case of inverting amplifier, what is the V naught upon Vi is basically minus Rf by R1, right? So this is the amplification factor, okay? So from the fact that we know, okay, and now what you have to do, you have to equate these two. So there are two inputs basically, V negative and V positive. So we can apply superposition. We can determine this amplification factor and equate them, right? So let us apply. So by superposition, okay, consider what? Consider V minus, okay. So and V plus will be grounded. V plus is grounded, right? And ground it, no problem. So your circuit becomes what? Your circuit becomes like this, minus plus This R will not come into picture now, but this guy is grounded, right? Okay, and this is 15K, right? Yes, this is 15K, this is 10K, and this is 22. Okay, 22K V naught, and here the V, this. What is V out? V out equal to V out upon Vi. I mean, this will be equal to minus of this resistance upon this, right? Already we know, right? So this can be written as 2.2, or you can say 22.10. Okay, this is first equation. Now second one is what? Second means you have to consider what you have. This is first. Second one is you have to consider B plus. Consider B plus, and Vi is okay. So your circuit becomes like this. This is grounded, and this will be like this. Okay, that becomes a non-inverting amplifier now. That becomes non-inverting amplifier. This is 10K, and this is basically the. So here the input is B plus, and this guy is what? This guy is your 22. Let me erase this 22 properly. Let me write. This is 22K. Now V naught. So V plus upon, you have to find V naught by V plus first. So you need to apply here the voltage division, so that you could find here, okay, because from the virtual sort, these two voltages will be same. So what is by voltage division? By voltage division rule, right? By voltage division rule. Why we are applying voltage division? Why we are applying voltage division over there? Because the op-amp does not take any current, right? Op-amp will not take any current, so these two resistors will be in series, right? So here it will be, you can say, at this point, what shall be the voltage? The voltage will be V plus times R upon 50, plus R, right? 50 plus R. So what you can do now, you can and here the total gain you can write now, total gain. So the V naught will be equal to V naught will be equal to what? V naught will be equal to or else you can do like this. Let me explain here. So this voltage that is V plus R into upon 15 plus R is across this. So you can divide, you can apply the voltage division rule, right? Because you can see the voltage across this guy will be what? V naught times 10 upon 22, 22 plus 10, right? So you can write here that V plus R equal upon 15 plus R equal to what? V naught into 10 upon 22 plus 10, that is 22 plus 10, that is 32. Okay, 32. Okay, so this is okay. Now what you can do here is you can find the V naught by V plus. So V naught by V plus will be equal to 32 by 10 into R by 15 plus R, right? So this is the amplification factor, right, for second equation. So now what you can do, equation 1 and equation 2. Okay, so from equation 1 and equation 2, very good problem, right? So you can equate this amplification factor and you will get the answer R. Yes, so you will get the answer R as what? Please try to solve this question. Okay, so you can see here we have found equation 1 as minus 22 by 10. Okay, and then we have considered what? So you will get what you have to equate with what? I mean, this negative sign you don't have to take. Okay, amplification factor means you have to equate mod of that. Okay, so you'll get answer as 33k. Okay, so you can equate here. So equating both side, I mean equation 1 and 2, that is 22k upon 10k equal to, you can take mod of that, right? Mod of this, and here already I've told you. Okay, that is 1 plus you know, you can write this as, okay, let me directly solve this. So let me forget about this. Okay, 32 upon 10 into R by 15 plus R. Okay, so once you will solve this, what you will get here is that you will get R as 33k. Okay, so this was very good question, right, from Op-Amp. So I hope this is clear for everyone. Okay, you can see here what we have done in the circuit. So you need to identify, you need to know that what is going to be the gain of inverting amplifier, what is going to be the gain of non-inverting amplifier, and so on and so forth, right? So let me take more questions. So we are taking questions from Op-Amp only, and then we will take questions from Mosfet as well. First of all, we will discuss three important concepts of Mosfet, and then we will okay, right. So one of the very important problem which was asked in GATE 2013, right, was let me take that problem because that problem is very good problem. Okay. Yes. That GATE 2013 problem, right? So let me draw that circuit. In the circuit shown below, right? In the circuit shown below, okay. What is the output voltage? What is the output voltage? Guys, so you have to learn how I'm solving the problem, right? So the approach is very important. Despite you know the solution, you know the answer, but the approach is very important because you must be able to solve questions in a smart way, right? So in the circuit shown below, what is the output voltage? Voltage V out, right? If the silicon transistor Q, if the silicon transistor and an ideal op-amps are used, okay, if silicon transistor and ideal op-amps are used, right? So they have mentioned that there should be silicon transistor, right? So let us see. Okay, for silicon transistor to turn on, what shall be the voltage? The voltage shall be 0.7 across base and emitter, right? So that important concept you must know. Okay, so let me draw the circuit here. So in place of diode, they have put transistor, right? Nothing else under inverting mode. So because we have seen that the combination of what diode and op-amp, because we wanted to make the diode ideal, right? Here also they are trying to make the transistor ideal. So here you can see this is basically 5 volt and this guy is 1K. Now there is a transistor connected to it, right? So this is a transistor, okay, and there is a V out and your base terminal is grounded. Your base terminal is grounded. So in order to turn on the transistor, what voltage we need here? That voltage we need is 0.7. So once there is a 0.7 voltage, so what shall be the V out? Okay, this terminal should be what? Negative. Okay, so this transistor will be on. This is negative, this is positive. Okay, so you can apply simple KVL from here to here, right? From here to here, okay, plus to minus. So from here to here by KVL, So what will be 0.7, okay, plus V out equal to 0. So V out will be what? V out will be minus 0.7. So this was the answer for this question. This was very good question, right? And they have also given the supply plus 15 volt, minus 15 volt, right? All these things. What they have given this, so that if this transistor will not work, okay, so this entire op-amp will behave like a comparator, okay. So answer will be either plus 15 or minus 15, right? So they have given options here. So let me write the option as well for this question. So option A, option B, option C, and option D. So option A was given as minus 15. See how miracle they have given, right? How confusing options. And this is 0.7 volt. This is plus 0.7 volt. And there is a plus 15. Right? So they are given 0.7 or 15 either. Okay, so if this op-amp will be have like a comparator, then answer will be negative 15, right? But this op-amp will not be have like a comparator. Reason, your transistor is on, so if the transistor is on, the answer will be minus 0.7, right? And if the transistor will not on, then this answer will be if the transistor will not be on, then the greater the potential at inverting terminal, the answer will be negative of that, negative supply. So I hope this is clear for everyone. So the answer for this question will be B option. Right. Very good problem, which was asked in GATE 2013. Right. Slew rate problems we have already covered, right? And what one question was asked, from the op-amp, the circuit shown in the figure is that of. So you have to identify, okay, the circuit shown in the figure. Shown in the figure. Is that of. This is minus, this is plus. There is a V in, right? And okay, so this is going to be your R2 and this is V out, right? And this is R1. Now in the options, what options they have given is option A, they have given here option B, option C, and option D. Okay, so you have to choose. Okay, the circuit shown in the figure is that of. Okay, so option A they have given is a non-inverting amplifier, a non-inverting inverting amplifier. Okay, option B they have given is an inverting amplifier. Okay, an inverting amplifier, right? And option C they have given is an oscillator. Have the negative feedback. Okay, but this here you can see there is a minus and plus. Okay, so and okay, so if you will try to determine what kind of feedback it has, so it will be having positive feedback, right? Okay, and don't think that if we are connecting output to the positive terminal, that's why there is a positive feedback. No. Okay, so remember this op-amp will not be functioning like the non-inverting amplifier or inverting amplifier. And yes, oscillator also needs what the positive feedback, but the thing is they have given here the input, and this there is no capacitance or inductance right here in the feedback. For the capacitor, for the oscillation, right, there should be L, at least LC kind of. Okay, so this cannot be the answer as well, right? The feedback network should be having RLC, and so this will be the Smith trigger, right? So remember, this is a Smith trigger. Okay, the circuit shown in the figure is this is the Smith trigger circuit, remember. Okay, because Smith trigger will be having the positive feedback, right? Okay, so let us take one more problem from the op-amp circuit only. In the circuit of the figure, V naught is, okay, in the circuit of the figure, V naught is, right? So they have given the op-amp circuit only. They have given the op-amp circuit here, right? Minus plus, there is R, there is R, okay, there is a V naught, and this guy is grounded, right? This is grounded, and the input here is plus 1 volt, right? Input here is plus 1 volt, and this is plus 15 volt, and this is minus 15 volt. Okay, this question is very good question. If you see, okay, and in the circuit the V naught is, okay, so in Haribari, if you see, right, option A, option B, option C, and option D. So if you are not able to identify what kind of feedback it has, and if you start solving the questions, you will say the answer is -1, but the answer will not be -1 for this question. Okay, answer will not be -1 for this question, right? Uh, because this op-amp is under positive feedback. Okay, this op-amp will be under positive feedback. So this will behave like a Smith trigger, right? So output will be what? Your output will be different. Okay, your output will be, or you can say this will behave like a comparator, right? So the options given are here. You can see this is 1 volt, and this is option B, that is 2 volt, right? And option C, there is a plus 1 volt, right? So many of you might give the answer -1 because you might think this is a amplifier and the inverting, this is an inverting amplifier, right? So the answer will be minus R by R, okay, but the answer will not be -1, remember. And so possible answer can be what the maximum answer, because see, this terminal is higher than this terminal, okay. So the output of this circuit will be what? Output of this circuit will be, option A will not be correct here, remember. Option C will not be correct, okay. This is very good question, I'm telling you, right? And this question was asked in GATE 2000. Now, nowadays, based on these problems, they are framing questions. If you are able to solve questions very carefully, so you can tackle any problem, right? So this problem will not take more than, you know, yes. So the circuit shown here, this kind of circuit shown here is a what? Regenerative comparator, right? This is a regenerative comparator, or Smith trigger, you can say. Regenerative comparator. Okay. So it is a comparator with positive feedback, also known as what? The Smith trigger, right? So the answer will be what? 15 plus 15. We will compare, this is 0 and this potential is high, so output will be saturated. Understand? So I hope this is clear for everyone. So don't give the answer these, okay? Answer will be plus 15. Very good problem this was. Okay. Right. One more problem from the GATE exam only, that GATE 2016. uh, the op-amp has finite open loop voltage, right? Yeah, the op-amp has finite open loop, okay, open loop voltage gain. Open loop voltage gain of 100, right? Its input offset voltage, its input offset voltage, right? Its input offset voltage, that is VIOS, right? VIOS is given as plus 5 millivolt. So this is very good question. This can be asked in HAL examination, right? From non-idealities, right? The op-amp has finite open loop gain, voltage gain of 100, and its input offset voltage VIOS is 5 millivolt. Okay, is modeled okay, is modeled as shown in the circuit below. Shown in the circuit below, right? The amplifier is ideal in all other respects. The amplifier is ideal in all other respects, right? V input they have given is V input which is equal to 25 millivolt, right? So this is a question asked in GATE 2016 by IISc Bangalore. So the answer, okay, so what they have given here is the op-amp has finite open loop gain, that is 100. Its input offset voltage they have given is 5 millivolt, is modeled as shown below. So let me draw the circuit, because unless we draw the circuit, we can't understand. So we have to find output voltage in millivolt, right, for this circuit. This is very good circuit, that is minus to plus, and there is 100 volt, that is, open loop gain they have given, and plus minus and plus minus, right? So they have given V input as V input here, and VIOS, that is input offset voltage, is given as 5 millivolt, right? And they have given this under non-inverting stage, right? So this is 1K, you can say this is 1K. What about this? So let me draw properly. This is 1K, and this guy is 15K, right? And this is V out, right? Okay. So VIOS equal to 5 millivolt, and V input is also given as 25 millivolt. Can you tell me how we can solve this question? Okay. So this question is very good question, and this question was asked for 2 marks. Right. So what shall be the output voltage? You have to find the output voltage in milli voltage. You have to find. Okay. And you can go through the question again. The op-amp has finite open loop gain 100. Its input offset voltage VIOS is plus 5 millivolt, is modeled as shown in the circuit below. The amplifier is ideal in all other aspects, and you have to find what output voltage. So how can you find the output voltage? You can find directly, right? You can find directly because it is a finite gain. It is having finite gain. So please do not apply any sort, what we can say, any virtual sort and kind of a concept, because these two potential will not be at the same potential. Okay, these two node will not be at the same potential, because okay, so you have to keep in mind that you can solve this question by with the help of V out equal to, as we know, that A times V plus minus V minus, right? Potential at V plus minus potential at minus, right? As we know, this is the output, okay, for any op-amp. So here we can say that V out equal to A is 100, and what is V plus? V plus is basically what is the potential at V plus here? So at this point V plus, what is the potential? You can see that is 30 30 millivolt, right? So here you can write that is 30 millivolt minus the potential at this point is what is the potential at this point? V out, okay, upon 16, right? Because 15 plus this. So you can write here that is V naught plus 15, 16, right? Okay. Now you can equate this, okay? So your V naught common, so 1 minus 1 by, 100 by 16 equal to 3, right? Okay. So from here you can compute V naught equal to 3 by 16 minus 100 into 16. So 48 upon, you can calculate this, right? What answer you're getting here is, I think, okay. So this is coming here, this side, this will come plus, okay. So please take care of this. So this will be like this. Okay, so here it will be 116. Okay, so 48 by 116. You will get 48 by 116. So your answer will be approximately 413.79, millivolt. Okay, once you will compute this. Okay, so please keep this in mind. Okay, when you are taking this side, okay, so it will be positive, right? And this is very easy question. So this problem is where the gain is what? Where the gain is finite. Understand? So this problem is very good problem, right? Anyone can solve this kind of problems. So slight calculations, smart way of solving. Okay, these are very good problems. So let us take more problem from op-amp circuit, right? So let us take this. Uh, was the problem. Okay, you can solve this kind of problem. So find the output voltage of the following circuit, right? Find the output, find the output voltage of the following circuit, assuming ideal op-amp behavior, assuming ideal op-amp behavior. Right? Find the following circuit, assuming the ideal op-amp behavior, right? Ideal op-amp behavior, remember. So a circuit is slightly big. Okay, so just I will draw the circuit, you can solve yourself. I will hint you, okay, how to solve the circuit here. So they have got two op-amps back to back, right? So one op-amp is this, that is minus 2 plus. Okay, see how so if you have attended my class, so these questions can be done very confidently. You don't need, now they have said that the op-amp is ideal, so you don't have to worry about anything, right? So this problem become very easy problem. This is 4K. There is a op-amp again from minus to plus, and there is a 1 volt connected, and this guy is directly connected to output V naught. Okay, very beautifully designed circuit. Okay, and right here this guy is again 1 volt, and this is 1K. There is a 2K ohm, there is a 1K, and there is a 7K. Right, and this guy is basically 8K. So you have to find what? You have to find the output. You have to find output. Okay, voltage. Let me erase this and write again. You have to find the output V out of the following circuit, assuming ideal op-amp behavior, right? So can you help me to find? Can you help me to find? So you can determine the potential at this point as well. So what will the potential at this point? It will be V naught by 8 by voltage division. Okay, and this 1 volt is here, right? 1 volt. There will be 1 volt here. Okay, 1, right? And so you can find the potential at this point now. At this point, you can find the potential at this point. So you can easily calculate the problem. I mean, you can easily calculate the output here, right? So this is how I'm hinting you how to find the output of this kind of a question, right? So try to solve this question within 40 seconds. So you will enjoy this, right? Okay. So I hope this is clear. Okay, so at this point, this is VA, right? I mean V naught by 8, and you can apply at this point what you can apply the superposition. Okay, you can apply superposition here, and you will get okay. So your answer will be directly. I'm just giving you the answer, so you can solve this question. Okay, so the answer will be 4 volt. Please try this question. Okay, because I've told you everything. Ideal means you can apply virtual short concepts, right? And how did I write V naught by 8? Because these two are in series, because the current it will not take. This V naught by 8 will be here. Okay. And the current which will be flowing here, 1 minus V naught by 8 will be flowing through here, right? And then you can find the potential at this point, right? So the potential at this point you can find, you can say VA, right? The moment you will find the potential at this point, so the current you can find now, and this current will be flowing here, right? So very easy problem, right? So anyone can try. So find the current and go like this. So the V naught will be 4 volt. Yes. Let us take more problem, based on op-amps. Okay, so one problem is from op-amp compensation, right? So question is from op-amp compensation. The amplifier circuit shown in the figure is implemented using compensated op-amp, right? So this problem is from op-amp compensation. This topic is very important. Op-amp compensation. Okay. So the question says here is that the amplifier circuit shown in the figure, the amplifier circuit shown in the figure, right? Shown in the figure is implemented using uh, compensated op-amp. Okay, compensated op-amp, and has a open loop gain A naught, and has open loop gain A naught, that is 10. Okay, 10 is given, that is like this, 10 raised to power 5 open loop gain, sorry, 10 raised to power 5 open loop gain, high open loop gain. Okay, and the open loop cutoff frequency also, and open loop cutoff frequency they have given, open loop cutoff frequency they have given here, open loop cutoff frequency they have given, that is fc equal to 8 hertz, fc equal to what, 8 hertz, right? The voltage gain of the amplifier, what you have to find here is that the voltage gain of amplifier at 15 kilohertz, okay, in EV is. So this is a problem, right? This problem is from op-amp compensation, and the amplifier circuit shown is implemented using compensated op-amp, right? So this is very important concept, right? You must know. Okay, so this problem can be asked in your exam. Has open loop gain, they have given high gain only, and the cutoff frequency this. They are asking gain, means they're asking closed loop gain at, they're asking closed loop gain at 15, right? So they have given circuit as well. So let me draw the circuit. So the circuit looks like this. This is a circuit plus minus Vi. This is grounded, right? And from here it is connected here, V0. This is R1, that is 1K. Okay, that is 1K, remember. And this guy is 79K. This is under negative feedback only, right? So this is a circuit, and what they are asking is they are asking V0 by Vi at 15K क्या होगा? What will be, okay, 15K. So can somebody solve this question? Can somebody try this question at least? This question was for 2 marks only, right? 2 marks. Yes. Yes, so let me go through the question again for you all. The amplifier shown in the figure is implemented using compensated op-amp and has the open loop gain, right? And has the open loop gain, and they have given the open cutoff frequency fc equal to 8 hertz, right? The voltage gain of amplifier at 15 kilohertz, right? So now the frequency has got increased here, so they are asking the closed loop gain at 15 kilohertz, right? So let us solve this question, right? So we have got two, we have got what? We have got two methods for this, right? One method will be very straightforward, right? I mean, you can solve this question with the help of two methods. Number one method we are going to talk about here is the method number one, right? So where you must know that the closed loop gain, whenever it is a function of frequency, can be written as what? A naught upon 1 plus S by omega cutoff frequency, that is omega P or omega C, whatever you want to call it, right? Omega C, right? This is op-amp compensation, right? Because of op-amp compensation, whenever gain is a function of frequency, closed loop gain is a function of frequency, so A naught upon 1 plus S by omega C, right? So this can be written as A naught is given as 10 raised to power 5 upon 1 plus S, right? S upon 2 pi fc, right? That is cutoff frequency, right? And from the given op-amp, you can find the gain. From the given op-amp, you can find the V, okay, you can find here from the given op-amp, what you can find, that is the what shall be the beta here, right? What can be the beta here, right? So this is V minus, okay, so beta is what? The feedback factor, right? You can say Vi equal to V naught by 80, right? Okay, so from here you can say Vi by V naught equal to 1 by 80 is the beta, right? You can say, or gain will be uh, reciprocal of this. Okay, so this is beta, right? Or you can say, okay, right? So now you can directly write or you can come this is, or you can also say what? You can also say here that V potential at inverting terminal is what? Not into 1 by 80 by voltage division, okay, or you can say V naught by 80, right? V naught by 80. So V naught will be equal to what? V naught will be equal to Vi minus what? V naught by AT into A times S, right? This is the output for any op-amp, right? So V naught is what? Potential at positive terminal minus potential at negative terminal into the gain, right? So now what you can do here is you can take the multiplication and take this V naught common here. So 1 plus AS by AT, right? AS by AT equal to VI into AS. From here you can compute V naught. Okay, V naught by VI. Okay, so let me compute here. V naught by VI. You will not be having any kind of confusion as well because I'm just deriving as well, right? So AS upon 1 plus AS upon AT. Okay. So how did I write this? This is a closed loop gain, right? So it can be also written as A upon 1 plus A beta. So this is a beta. Beta is what? 1 by AT, right? And this is AS. Here the gain is what? Gain is the function of frequency, okay? So now you can plug back this AS. You can plug back this AS. What is AS here? So this is the equation number 1. You can say this is equation number 1. So from the equation number 1, you can plug here. Okay, so right from the equation number 1, you can plug here everything. Right. So let us plug here everything. So it will be 10 raised to power 5 upon 1 plus S upon omega C upon S upon omega C upon 1 plus 10 raised to power 5 upon 80 into 1 upon 1 plus S by omega C, right? So you can solve this. You can solve this. This will be very easy now. So this comes out to be, you can write here, next step will be what? Next step will be 80 into 10 raised to power 5 upon this is 80 plus 80s upon omega C plus 10 raised to power 5, right? So this is the picture here, right? And now you can put this is what? This is V naught by VI, function of S. Okay. Now V naught by VI, or you can say A, will be what? Can be written. You can take the managed block 80 into 10 raised to power 5 upon this is the real part, right? So this plus this, okay, and you can take the square of that, right? So you will be able to get the answer very quickly, right? So you can plug S equal to j omega, S equal to j omega here. Understand? So what is omega C given in the question? Omega C was given as I mean FC was given as something. Okay, so that was what you can do here is once you will plug S equal to j omega, okay, and take the magnitude, so gain will be approximately equal to 44.36. So you can solve, okay, because here you can plug j omega and then plug at S equal to j times of 15. Okay. And so you will get answer as 44.36. It was very easy question, okay? This is method 1 and that is direct without making any confusion. Right. So let us talk about one very important concept, that is one important topic, that is MOSFET, right? Because I haven't discussed about MOS. So MOSFET, okay, and then we will discuss few problems. So MOSFET means the metal oxide semiconductor field effect transistor. So we will discuss about only one kind of a MOSFET, that is enhancement kind of a MOSFET, N-channel, okay, enhancement MOSFET, right? It is N-channel and it is P-channel MOSFET, right? And it is enhancement depletion, okay, depletion enhancement, right? So we will only discuss about the circuit part, enhancement, right? And this will be also depletion and enhancement, right? Depletion and enhancement. So if you have studied the physics part, so you can, I mean, the concept will be more clearer. But if you haven't studied, no problem, right? So the MOSFET is basically two kind of, right? It will be having three terminal as well, just like bipolarization transistor. And so we will just directly draw the MOSFET, N-channel MOSFET, right? So N-channel MOSFET. And we will not discuss about depletion kind of a MOSFET, right? So just we will take this kind of a MOSFET here. Okay. This is N-channel MOSFET, you can say, right? And because the arrow is at drain, I mean source terminal. So this is drain terminal, this is gate, and this is source terminal, right? And the potential between them, the gate and source, is VGS. The potential here is VDS, you can say, and okay. So this is what the picture here is, right? So we need to understand that, and the current will be drain current, okay, drain current. So there will be three region of operations, okay, there will be three region of operations. So let me discuss one by one, which will be used to solve the problem, okay. So region of operations. So this is a simple MOSFET circuit, right? And there is a voltage VGS. There is a VDS, right? You can write capital VGS, or yeah, like this VGS. So you know what? When the MOSFET will be on, one important parameter is that is threshold voltage, right? So the number one is, if your gate voltage VGS is greater than VT. If VGS is not greater than VT, remember, if VGS is not greater than VT, okay, what is VT here? That is threshold voltage. That is threshold voltage. If VGS is not greater than VT, remember, if VGS is not greater than VT, then the MOSFET will be in cutoff mode, will be cut off. Okay, it will not turn on, right? And the ID will be zero, and the ID will be zero. Simple. So you have to apply potential across VGS, okay, at gate terminal, at least greater than the threshold voltage, right? This is the first condition, right? That is the cutoff region. Next region is what? Next region is second. If VGS is greater than VT, if VGS is greater than VT, okay, if VGS is greater than VT, so you have two choices, okay. If VGS is greater than VT, the MOSFET will be on. MOSFET will be on. Remember, MOSFET will be on, right? But you need to find what? You need to find you need to compare the difference between this. Okay, the overdrive voltage will be what? Overdrive voltage will be VGS minus VT, right? Overdrive voltage will be VGS minus VT, and this VGS minus VT you have to compare with what? You have to compare with, if VDS is less than VGS minus VT, and if VDS is greater than VGS minus VT, right? So what you can say here is that if this is the condition, so the MOSFET will be in linear region. If this is the condition, the MOSFET will be in saturation. And for any MOSFET to behave like an amplifier, it must work in saturation region. So remember, first of all, you need to check whether your MOSFET will work or not, will be on or not, right? So you have to check the potential which is being applied at the gate terminal should be greater than the threshold voltage, right? Should be greater than the threshold voltage. Okay. Okay, remember, should be greater than the threshold voltage. Okay. And then you have two choices. You have to compare the difference between VGS minus VT with VDS. If VDS is less than VGS minus VT, then you can say that will be in your MOSFET will be in linear region. And if VDS is greater than or equal to VGS minus VT, so you can say that your MOSFET will be in saturation region. Okay, right. Now, what shall be the current then? If the MOSFET is in, what? If the MOSFET is in linear region, so if MOSFET is in linear region, then the ID will be, what are the conditions? First of all, your VGS must be greater than VT. Second condition, your VDS is less than VGS minus VT, right? Your VDS is less than VGS minus VT. Okay. So ID will be what? ID will be equal to 1 by 2. Okay. Wait. Your ID will be what? ID will be equal to, let me tell you, mu n cux W by L VGS minus VT whole square VDS minus VDS square by 2. Right? This is the equation you have to keep in mind. Let me write again. ID will be equal to mu n cux W by L VGS minus VT times VDS minus VDS square by 2. Okay, where this mu n is the electron mobility. This is the oxide capacitance. Okay. Oxide capacitance, right? That is epsilon Ox upon Tux. And this is the aspect ratio, right? Aspect ratio. Bits upon length, channel length, right? So ID equal to mu1 Cux W by L VGS minus VT into VDS minus VDS square by 2. Okay. Remember one important condition. Note, if VDS is far less than VGS minus VT, if VDS is far less than VGS minus VT, then ID becomes, then ID will be, okay, then it will, MOSFET will be in, then it is in triode region. Yeah, triode region, right? So triode region means what? Your MOSFET will be have like a resistor simple. So ID will be equal to mu n Cux WIL VGS minus VT times VDS, right? Because you can neglect VDS square, right? So this is the important condition. You have to keep this in mind. Okay, so you can differentiate with respect to VDS. So differentiate it. So ID with respect to VDS so will be equal to mu1 Ux WL VGS minus VT. Okay, so from here you can say dou VDS by dou ID will be equal to what? 1 upon mu n Cux WL VGS minus VT. Right. So this will be RDS. Resistance in the triode region. So your MOSFET behaves like a resistor, okay, in the triode region. If VDS is far lesser than VGS minus VT, right? Remember. Okay. Right? Or you can say 2 times of what not, right? Whatever. Whatever you wanna call it, right? So this is the condition. MOSFET, here you can write MOSFET behaves like resistor. If VGS is greater than VT and VDS is greater than or equal to VGS minus VT, then MOSFET is in saturation region. Right? MOSFET is in saturation region and then MOSFET is in saturation region and your current equation ID will be equal to half mu1 Cx WL VGS minus VT whole square. This is very important equation, right? You have to keep this in mind. ID equal to 1 by 2 mu1 Cx WL VGS minus VT whole square. This equation is valid only in case of saturation region. These are very important concepts, right? So if you're going to differentiate ID with respect to VGS, so you will get GM of the transistors, right? What you will get? You will get GM of the transistor, right? So what you can do here is you can differentiate ID, okay, do VGS, right? So what you will get here is that you will get mu1 Cux WIL VGS minus VT, and this is equal to GM of the transistor, transconductance. Okay, mu1 Cux WIL VGS minus VT, that's it. Because you are differentiating with respect to VGS. So VGS is very important. Okay, I mean GM of the transistor is very important, right? And if you will differentiate with, I mean, if you want to differentiate with respect to what with respect to VDS, then what will happen here is that you will have to consider the channel length modulation, right? So here right now we are not in this case there is no channel length modulation, right? But if you will consider channel length modulation as well, so yeah, you can write here, consider this channel length modulation, length LE, okay, channel length modulation your diode, your drain current will become 1 by 2 mu Cux W by L Vgs minus Vt whole square 1 plus lambda Vds. Okay. Now this equation can be differentiated with respect to Vds. So you will get resistance then. Dou Id by dou Vd is equal to, basically this is a current, right? Id sat you can say. So Id sat can be kept as it is times lambda. So if you take the reciprocal of this, right? So what is this? This is basically 1 by R ds, okay, equal to id sat lambda, right? So here RDS is equal to what? RDS equal to 1 upon lambda times of IDS sat, right? So this is what the resistance is, okay, whenever there is a lambda is not equal to 0, remember. And if somebody is going to ask you what is okay, so please keep this in mind. If someone is going to ask you what is the dimension of this lambda, so you can check here, okay, you can compute from here dimension of lambda. Lambda is a channel length parameter, right? So lambda equal to 1 upon RDS into ID sat, that is the voltage. So lambda is having voltage inverse, right? It is having voltage inverse, right? Unit. So whenever this will be given, okay, we equal to IR, okay. So please take care of this. So if I draw the IV characteristic of a okay, so ID versus VDS, right? ID versus VDS, right? So what will happen here is that at high, initially we want this kind of a characteristic, right? But there should be slope as well, right? So you have to keep this in mind. As you change VGS, you change VDS. So because of channel modulation, there will be a resistance, output resistance, okay? So these are important, okay, and your MOSFET behaves like an amplifier. Behaves like an amplifier when it works in saturation region. Right? These things you have to keep in mind. Now let us talk about a small signal model of the op-amp. And not MOSFET, right? So a small signal model of MOS. So suppose this is a MOS, right? Let me draw here MOSFET, right? Just common source, right? This is a common source kind of, right? And this is RD and this is plus VDD, and there is an input applied, and you have to find the out, right? So you can draw the small signal of this. So how can you draw? As we know that the input resistance will be infinite, okay, because of this oxide, so there should not be anything. So Here the quantity will be simple plus VGS, small VGS, and here there will be a current, okay, that is GM VGS, okay. And if there is no, suppose this guy is, I mean, okay, if suppose this guy is not, this guy is present, okay. If this guy is present, right? So let me correct here. Somewhere we have done mistake, I think. Okay, let me go back. Somewhere lambda, I think we have taken lambda like this. Okay, let me check. Hmm. Here only we have taken, yes, this. So there should be infinity, right? If it does not equal to infinite, if it does not equal to infinite, right? Infinite means what? If it is infinite, then there is no, it is zero only, right? If it does not equal to zero, right? If it will be equal to zero, then RDS will be open circuited, right? Okay, right. So if lambda it does not equal to this, okay, so please keep this in mind. What I was talking about here is, yes. So as I have taken this circuit, 1 minute. Small signal model of the MOSFET, right? So this is simple. So right now we are not considering this guy, right? It's channel and modulation. So directly you can connect this actually, in case of AC analysis, this part will be grounded, right? So here you can connect directly RD, and there will be output, right? Output will be across this, okay? And there is an input VI. So you can compute now. This total current is flowing like this, right? From plus to minus. So your V out will be equal to minus GM VGS times RD. And where VGS is what? Where VGS is VI. So your gain V naught upon VI equal to minus GM RD. It is very simple, right? Minus GM RD. So if this is a amplifier, right? Let me draw again. And someone is asking you to compute the gain, right? So let me tell you the trick here, that is VDD, RD, and VI. So you don't have to draw anything, right? Because you know that V naught equal to what? V naught by VI, you have got minus GMRD, right? So what you can do now, you can further rewrite this, okay? So you can further rewrite this as minus RD upon 1 by GM, right? So what you can say here is that this is a resistance, okay. This is a 180-degree phase shift, right? This is a resistance looking from this terminal, right? If you look, or you can say, let me erase this again. When you will perform AC analysis, so you will have to ground this, right? And there is a V out. So if you will see from here, right? If you will see from here, so you will see only from this point, output point to the ground, there is a resistance R, right? And if you will see from here, right, so you will get the resistance 1 by GM. So taking the ratio of these two give you the gain, right? So if you will see the resistance from, okay, from the source terminal, that is source terminal, this is green gate terminal, and this is drain, right? So you can directly find the gain of this transistor, right? So let me take few examples again. Suppose you have got this kind of a circuit, right? Plus VDD, this is RD, and this is input. If you are finding, if you will find, if you will see from here, right? So what shall be the impedance? 1 by GM, and this is V naught. And if you will see from here to the ground, so there will be RD, right? RD is only there, right? So your output upon input, that is the gain, and there will be 1 degree phase shift because you are applying at gate and taking the output at drain. So source is common here, so this is common source. So RD upon 1 by GM. Right? Here this source resistance is not present. Suppose there is a source resistance. So you can write here the common source with source degeneration, right? Source degeneration. So then what shall be the gain here, right? So you can see here, this is the picture. There is a RS present. Now you have to write direct gain, right? You have to write direct gain. This is VI and there is a V naught. There is RD. So what shall be the gain directly? The gain will be V naught by Vi equal to minus. You know, there will be RD here, okay? Because if you will see the ratio of impedance looking from this point to the ground upon the looking from here to here, right? You have to see this time you have to see from source terminals 1 by GM, and if you will see from here, so it will be 1 by GM plus RS, because now this RS is coming into picture. So 1 by GM plus RS. This is a gain for this common source, right? So this is how we try to find the gain of any kind of amplifier in BJT as well as in case of Mosfet. So in case of Mosfet, finding gain is very easy. In case of BJT, finding gain will be quite difficult. Understand? Right. So please take care of that. Let me show you more circuit. Suppose this kind of a condition is given. Vi, and here the capacitor is given, and one this is RL, and there is a voltage V out, and there is a VDD. This is RD, and they are asking about what is gain on this transistor. What you will do here is you will ground this, you will sort this, okay, and you have to see RD here, right? And you have to see from here, this point to ground, from this point to ground. So these two resistances RD and RL are parallel, right? So V naught by VI equal to minus times RD parallel RL. See how fast I'm doing. So if you are looking from the source terminal, so you will get 1 by GM as a impedance, and if you're looking from this point to 1 by GM plus RS, because this is a source degeneration case, the resistance is present at the source terminal, so it will be 1 by GM plus RS. Okay, very good questions, right? Very good question. So let me try one or two questions. In case of BJT also you can do like this, right? Suppose in case of BJT, bipolar junction transistor, right? Suppose any BJT is there, right? Common emitter is given, and there is a VI, RC, VCC, okay? And if they are asking about the gain, so what shall be the gain here? The gain will be basically, what shall be the gain? So the gain will be basically, V naught by Vi will be equal to minus GMRC. Okay, this time transconductance of the bipolar junction transistor. What you can write this as minus RC by 1 by GM. Okay, it is very easy. So if you're looking for impedance from this point, so it will be 1 by GM. Okay, if there is no base resistance, right, it will be 1 by GM, and this will be grounded, so you can say the total resistance is RC, right? Suppose transistor is emitter is degenerated, emitter is degenerated, okay, emitter is degenerated, right? Suppose the meter is degenerated, okay, so what will happen here is that this RE will be present here, right? And this is RC, this is VI. Okay, so suppose this kind of a RE and RC is there, right? And this is V out, and there is a VCC, right? So if someone is asking what is the gain of this transistor, so directly you can write, if you look from this emitter terminal, so you will get 1 by GM. If you look from here, okay, so you will get 1 by GM plus RE, okay. And if you look from here to the ground, because after all the DC supply will be grounded, okay. So okay, and here there is no RB, okay, there is no resistance. Your base is not degenerated, remember, right? We have neglected the base term. So directly you can write the gain of common emitter. V naught by Vi will be equal to minus, because you are applying voltage at base and taking output at collector. It will be RC upon 1 by GM plus RE. You can see, right? This is very good actually way of writing the gain. Suppose base resistance is present, right? Definitely one question may be asked. Right? This guy is this, and that is RE as well. This is RC, VCC, okay, and there is a RB present. This is VI. Yeah. So what will happen now is that you will have to bring this RB this side. Okay? This RB will come this side. So what will happen? See, if this that will be RB, but this RB will come RB will beta plus one. Right? So mind all this. So here 1 by GM, 1 by GM plus RE, okay, and this RB will come also this side, right? So in series it will be, right? So what you can write here is that again this circuit 1 by GM plus RE plus RB by, okay. So these are very important concepts. These are very, very important concepts, right? And if someone is going to ask you what is the impedance of common emitter amplifier, suppose this kind of a circuit is given, and they're asking about the input impedance of this. This is Vi and this is V out, and there is a VDD. There is a sorry, not VDD. It must be VCC, right? And this is RC, and they are asking what is the input resistance of this. So in this kind of amplifier, we directly R pi. R pi, because this will be the R pi beta, GM, GM beta. This is GM VBE, okay, and there is RC, okay, and there is a VBE. R pi, R pi model, okay, this is R pi model, or you can say beta, whatever you want to call it, right? GM VBE, right? So VBE basically equal to directly connected, so VI, right? And it is V naught. So if someone is going to ask you what is R input, what impedance you are looking at here, that is R pi. Okay, without this R. If that, if ammeter is degenerated, okay, if ammeter is degenerated, then what will happen? So this question is also asked most of the time. If R is, and so voltage gain will be reduced, but input impedance will be increased. So you see here, just I'm telling you that. Suppose this guy is present here, RE, and this is RC, right? And you have to see the impedance from here, RIN. So your RIN initially was what? It was R pi, right? Plus this RE will be transferred to that side, right? This RE will be transferred to the base terminal, right? So how it can be transferred? It will be RE times 1 plus beta. It will be RE times. So this is a boost, okay? This is a boost. If RE is present, so your input resistance will be increased by RE times 1 plus beta. RE times 1 plus beta. Okay, you have to keep this in mind. How it is happening, you know that. If there is a current IE, so IB will be what? IB will be IE upon 1 plus beta, right? If current is decreasing by 1 plus beta, so your resistance will increase by factor of 1 plus beta, right? So you have to keep in mind, because current and resistance are reciprocal to each other. See, this I is here, IB will be I upon 1 plus beta, right? So if RE is here, if RE is present here, so what should be RN here? RN will be, you have to understand, RN will be what? RE times 1 plus beta. Okay, so this is very important concept for everyone. And if RB is also present, then you have to consider RB as well. But you have to keep this in mind. So these are important note. Suppose this is a circuit. What is the resistance looking from this point? That is 1 by GM. And if this is a circuit, what is the resistance looking from this? That is R pi. Okay. And if this is a circuit, so what is resistance looking from this? That is R pi plus RE times 1 plus beta. So actually, you must know that R pi plus RE times 1 plus beta, right? Okay. So you can see this was the model for you know, for BJT, that is GMVBE R pi model. Now R pi beta model, if you want to draw, then you can say this is R pi and this is beta IB, right? Same thing. VB beta IB. Okay, so this GM VVE upon IB, small IB, that is base current, is equal to what? Beta. So VM by, you can see VM by VBB upon IB is equal to what? R pi, right? Because here it is VB and your current is flowing IB. You can say that the very important relation GM R pi is equal to beta. This is GM times R pi equal to beta. These, and if there is no early effect, so this output resistance will not be there. If there is a early effect, then you have to consider, right? Remember, okay, if early if is there, is present, right? So R pi model will be what? R pi model will be looking like this. GM VB, यहाँ पर क्या रहेगा? There will be R naught, right? This is R pi plus minus, okay. And the same model you can, R pi beta model you can say beta IB. In place of GM, you can replace beta. The current will be IB, controlling parameter. Now this current, this is BB controlling parameter, right? R naught. So this is R pi model. This is R pi beta model. So though in the examination you don't need to draw these things, right? You don't need to draw these things, right? And important note is what? Important note is that the GM of the transistor will be, your GM of the transistor will be, always keep in mind, IC upon VT. IC is what? IC DC. IC means DC collector current. DC collector current. And VT is the thermal voltage. Otherwise, in case of devices, we take 26 kind of at the rate. Whenever question will be there, you by default take. So if you plug GM equal to IC by 25 millivolt, so it will be giving you 40 time IC. So finding gain will be two-step process, right? Finding gain will be two-step process in case of BJT. First step will be, okay, finding gain is what? Two-step process. Two-step. Finding gain in two-step, right? Number one, find IC. Second, find IC DC from the DC analysis, right? And then AC analysis. AC analysis means this is from the DC analysis, right? Analysis. And AC analysis means GM equal to 40 time IC. If VT is 25, and directly then write the gain, then write the gain, right? As discussed. numerically, so we will get everything. Understand? Let me take one problem from, okay. So yes, what I am trying to convey here. We'll try to find the small signal gain of the transistor, okay, and yes, okay. So let us take one problem that is in the gate examination. It was asked, and we have to find the small signal gain of the transistor, right? Okay, very good problem. Suppose this kind of a transistor is given, this kind of a circuit is given. So I'm just going to give you circuit here. Okay. And there is a voltage divider plus VCC. There is a capacitor connected. So you can forget about capacitance in AC. Short circuited, right? So this is V0, this is VI, common emitter. So no problem. 1 micro, this is 1 microfarad, 1 millifarad, right? Only you need to understand this is 33K and this is 11. Oh, K, and this guy is 10. This guy is 1K. Okay. In AC analysis, this 1K picture will not 1K will not come into picture, right? But in DC analysis, open all the for DC analysis. Okay, because the first is DC analysis and you need to find IC. So, and there is no beta given, so you can say beta is high, right? Open circuit all cap and consider beta high, right? So neglect IB equal to 0. Okay, this is the in concept. IB, okay, so you can forget this, okay, just forget this. So what shall be the voltage at this point? Voltage at this point will be VCC is given as plus 12 volt, right? So direct you can answer because IC is not given, means you have to find IC. So 12 into 11 upon 44. So this will be 4 and this 3. So this is 3 volt and plus my 0.7. So this guy come down, okay. So this is 2.3 here, right? Okay. Yes. So that is what the 3 volt, I mean 2.3, okay. So you have to keep this in mind, very important, right? And then you can find IE, right? I mean, because neglecting beta, if beta is not given means you can neglect beta, right? Beta is not given, okay. So, or if you will consider beta is 200 approximately in the question, I think beta was, let me check whether beta is given or not, right? So in the question, they have mentioned that uh, uh, let me check. Yes, beta was given, right? If the beta is 200, right? So it's okay, but right? Because beta it is very high, and your VT is also given as 25 millivolts. So you can consider GM is what? GM is 40 time IC. The moment you find GM and all, gain will be, so you will get simple, right? So just compute here 2.3 by, it will be approximately 1000 compared to 10 means you can neglect. So it will be 2.3 here. It will be 2.3 milli ampere current will be flowing, right? And that will be IC. So GM will be 40 times 2.3, right? Okay, so IC will be, IC will be approximately equal to 2.3 milliampere, you can say. Your GM will be what? GM will be 40 times of IC, that is 2.3 millisiemens. You can multiply and you will get something, right? Now, what shall be the gain of this transistor? Because IC we have got, and GM we have got. So what shall be the gain of that transistor, right? So let me draw the gain, write the gain for that transistor. So in case of AC analysis, right? In case of AC analysis, what will happen? In, in case of AC analysis, you have to keep in mind that capacitor will be short circuited. In AC analysis, cap short circuited. Right? Just capacitor short circuited means what? Just forget about everything, right? And beta is high means you can neglect RB as well, means that, okay. So you can directly write this, okay. This is 10. And there is, let me check the circuit here. Yes. There is a 5 pin, okay, and this guy is grounded. There is a V out. What is gain here? V out upon VI equal to minus of 5000, because this is 5000, right? Plus 5000. Just forget about this plus minus because already you have taken this. And from here, if you will see, that is 1 by GM. And from here, if you will see, that is 1 by GM plus 10. So 1 by GM plus 10, right? So you can compute now, right? So once you will compute this, so you will get approximately the answer as, let me tell you the answer directly. You can compute that, right? Your answer will be approximately minus 232.23 approximately, right? Compute this, okay? So please keep this in mind. If beta is pretty high, you can neglect it, right? Approximately you can answer, but if beta is not high, then consider that, okay? So that is what the thing is. Thank you so much. Keep practicing, keep IQs of previous year questions, right? PYQ of gate and IES. PYQ gate and IES. Okay. Gate, okay, and IES PYQ. And we'll also conduct some mock tests for the HL. Thank you so much. We'll catch up next day for different subject. Thank you.